Riemann sums are a fundamental concept in integral calculus that allow us to approximate the area under a curve using rectangles. This powerful technique forms the foundation for understanding definite integrals. Let's visualize this concept with a simple function. Here we have a curve representing f of x, and we want to find the area underneath it between 2 points. We define our interval from point A to point B. The goal is to approximate the area under the curve between these two boundaries. To approximate this area, we partition the interval from A to B into smaller subintervals and draw rectangles within each subinterval. Here we start with 4 rectangles. We partition the interval by dividing it into n equal subintervals. The width of each subinterval is delta x, which equals b minus a divided by n, where n is the number of rectangles. The height of each rectangle is determined by choosing a specific point within each subinterval. We can choose the left endpoint, right endpoint, or midpoint of each subinterval. The Riemann sum is expressed mathematically as the summation from I equals 1 to n of f of xi star times delta x, where xi star is the chosen point in the ith subinterval. Here's the key insight. As we increase the number of rectangles, making them thinner and thinner, our approximation becomes more accurate. As n approaches infinity, the Riemann sum approaches the exact value of the definite integral. This fundamental concept bridges the gap between discrete approximations and continuous integration, making Riemann sums essential for understanding calculus and its applications in physics, engineering, and many other fields. We'll demonstrate Riemann sum calculations using the function f of x equals x squared on the interval from 0 to 2, divided into 4 rectangles. First, we calculate delta x, which is the width of each rectangle. Delta x equals b minus a divided by n, which gives us 2 minus 0 divided by 4 equals 0.5. This creates 4 subintervals, 0 to 0.5, 0.5 to 1, 1 to 1.5, and 1.5 to 2. Let's start with the left Riemann sum, which uses the left endpoint of each subinterval to determine the height of each rectangle. For the left sum, we evaluate f of x at equals 0, 0.5, 1, and 1.5. This gives us heights of 0.25, 1, and 2.25. Multiplying each height by the width 0.5 gives us areas of 0.125, or 0.5, and 1.125. The total left Riemann sum is 1.75. Next, the right Riemann sum uses the right endpoint of each subinterval. For the right sum, we evaluate f of x at x equals 0.5, 1, 1.5, and 2. This gives us heights of 0.25, 1, 2.25, and 4. The corresponding areas are 0.125, 0.5, 1.125, and 2. The total right Riemann sum is 3.75. Finally, the midpoint Riemann sum uses the midpoint of each subinterval. For the midpoint sum, we use midpoints 0.25, 0.75, 1.25, and 1.75. The heights are approximately 0.0625, 0.5625, 1.5625, and 3.0625. This gives us a midpoint Riemann sum of 2.625. Comparing our results, the left sum gives 1.75, the right sum gives 3.75, and the midpoint sum gives 2.625. The exact value of the definite integral is 8/3, or approximately 2.667. Notice that the midpoint sum is closest to the exact value. The different methods give different approximations because they sample the function at different points. The midpoint method is often most accurate for smooth functions. Upper and lower Riemann sums use the maximum and minimum function values in each subinterval. As we increase the number of rectangles, all methods converge to the exact value of the definite integral.
Knowledge can never replace friendship. I prefer to be an idiot.